NPRE 451 Final Exam Review. This review will be broken into 6 parts. Those parts correspond to the 6 major parts of our course. So the first part was radiation interactions and the basic physics. The second part were electronics and the pulse processing systems that we were going to use with all of our detectors. Then we hit on gas detectors, scintillators, semiconductors, and finally neutron detectors. So this will be a 6-part video series going through each of those sections, chapter by chapter, starting with the 2 key concepts for each chapter. We're going to use these key concepts to describe some important equations that go with them that will be relevant for your final exam. So I recommend going through your notes and looking at those 2 key concepts, or taking the sheet that I give you in class and following along. Here are our 2 key concepts for Chapter 1. Ionizing radiation comes in 2 major categories: charged particulate radiation and uncharged radiation. Number 2, ionizing radiation is typically created through the decay of an unstable isotope which can be mathematically described. So now we're going to try and come up with a couple of equations that are going to describe these 2 key concepts, so you can use these equations for your studying. And in particular, on number 2 here, where we talk about mathematically described, of course, the decay of an isotope is something that's easily mathematically described. So to describe radioactive decay, obviously we have a decay law, where if I have n is my number of nuclei, my change in that number of nuclei with time, n dot, or dn dt, is equal to some constant lambda times the original number, where lambda is my decay constant. And as we know, we can solve for this using the following relationship, where my number as a function of time is equal to my initial number of isotopes, and naught times e to the minus lambda t. Chapter 2 are how radiation interacts with matter as a function of the type of radiation, its energy, and what it is interacting with. Also, the mean free path of the radiation is the average distance between interactions and is also a function of the type of radiation, energy, and what it is interacting with. So the equations that we introduced in Chapter 2 started describing these radiation interactions. And first we talked about this concept called stopping power, S. And S, if you recall, is how much energy is lost per interaction. And that is the negative dE over dx, where dx is the path length and dE is the energy loss. Now, you remember we also described how we talked about this concept of mean free path, and we said that lambda is equal to the mean free path. And we had this idea that if I had a source intensity that I was trying to measure through an absorber, I could say that my intensity through the absorber was whatever my initial intensity was, I naught, times e to the minus mu e, mu of e times t, where t is the thickness, and mu is my attenuation length, where I can also say that mu is equal to 1 over the mean free path. It can be anything from specific type of interaction to a total probability. So we could have mu for Compton scatter, or we could have mu for total gamma ray interaction. But those are the 3 equations that describe Chapter 2. And now we have Chapter 3, the infamous chapter on counting statistics. So we have our 2 concepts here. There are 3 common probability distribution functions used in radiation detection: the binomial, Poissonian, and Gaussian distributions. The detector's count rate determines which distribution applies, as well as the expected standard deviation. And then number 2, in some very specific cases, the standard deviation in a single measurement can be determined by the square root of the measured value, but this only applies for non-derived quantities. For derived quantities, you must use the error propagation equation. So let's break this out now into some equations. So if I have n is equal to my number of trials, and I have p is equal to my probability of success, then I can write out the binomial distribution as p of x is equal to n factorial over n minus x factorial p dx times the quantity, let's see, 1 minus p to the n minus x. And we know that there's this thing called the average, or the mean, and here I'm going to have that be x bar, and this is my theoretical mean, not my experimental mean. X bar is equal to n times p. And then I also have this thing called standard deviation, which for the binomial distribution is sigma is equal to the square root of x bar times 1 minus p. Now that was just for the binomial distribution, but you remember we had approximations that we could make. For instance, if we had small and constant probability of success, little p, then we have the Poissonian distribution, where I have p of x is now equal to x bar to the x times e to the minus x bar that's probably not visible, this is an x bar, and that's divided by x factorial. In the case of the Poissonian distribution, we can work out that our standard deviation is equal to the square root of the mean. Okay, so that's the Poissonian distribution. Now, one further simplification is if we have small p but large x bar, so our mean is large, then we simplify to the Gaussian distribution. And for the Gaussian distribution, we have p of x is equal to 1 over the square root of 2 pi x bar times the exponent of x minus x bar squared divided by 2x bar. And the standard deviation, again, is the square root of the mean. So that is the Gaussian distribution. The last thing we need to talk about in Chapter 3 is error propagation. So this is all of key concept number 2. If we have a derived quantity, such as a rate, adding counts, subtracting counts, multiplying things together, ratios of things, you must use the error propagation equation. So if I have some unknown u, I could say that the standard deviation in that unknown u squared is going to be the partial of u with respect to some term x squared, sigma x squared, plus partial u, partial y squared, sigma y squared, plus partial u, partial z squared, sigma z squared, plus ... however many terms you have in your equation. When in doubt, use the error propagation equation. Write down the error propagation equation. It will only help you. And finally, we have Chapter 4, where we have our 2 key concepts. Radiation detectors quantify charge, but it is important to note this is done by measuring the current or voltage of a system during some time interval characterized by the RC time constant. And then we also have number 2, every detector can be characterized by its efficiency, energy resolution if applicable, and dead time. Each of these can be measured. So obviously, measuring the amount of charge created is a very important thing to do. So if I have my amount of charge is Q, this is equal to the energy deposited in my detector divided by W, where W is my average number of carriers, my charge carriers per electron volt. So if I'm talking current here, then I can relate my current, I, is equal to some rate. This is my source interaction rate or something like this times that charge, or this is equal to R times, here's E over W, and then I have little q, the charge of the electron, which is equal to 1.6 times 10 to the negative 19th coulombs, a number you should memorize. So that's if I'm measuring current. If I am, on the other hand, measuring voltage, my equation is V equals Q over C, where Q is my charge that's created, C is my detector capacitance. So, let's move on. We have things like resolution and dead time that we need to talk about. So the resolution is equal to the full width at half maximum of any peak in my spectrum divided by the centroid value of that peak. I can talk about my resolution being at the statistical limit. So this is the limit defined by Poissonian statistics. And this is equal to 2.35 times the square root of the Fano factor divided by n, the number of charge carriers created. This, if I wanted to write this in terms of energy resolution, this is 2.35 times the standard deviation in energy divided by the energy. Lastly, I had this thing called dead time. And dead time, we're going to have n, which is my true event rate. So this is what we should ideally measure. But m is my measured rate. Okay, measured rate, which is m is less than or equal to n, usually less than. So I had two dead time models to talk about. We talked about the parallelizable system, in which case we had m is equal to n times e to the minus n tau, okay, and the non-parallelizable system, is equal to n is equal to m over 1 minus m tau. Tau is a dead time. Okay, so no detector is truly parallelizable or non-parallelizable. They're usually some sort of mixture of the two.